So, welcome everybody. I am Daniel from Team Hungary, and I am going to present you problem number 12, the gyroscope Teslameter. The problem states that when a rotating gyroscope made from a conducting but non-ferromagnetic material, just like copper, is placed in a magnetic field, it will slow down. I have to investigate the relevant parameters of the deceleration. Relevant parameters are, for example, the material of the disk, the parameters, the geometric parameters of the disk, the parameters of the magnet, and the position of the magnet. So let's see the basic physical explanation for this phenomenon. We can say that when a disk is rotating in a magnetic field, the magnetic field is changing. Unless, of course, the magnetic field is homogeneous in all of the disk, or for example, if it's radially symmetric and is in the middle. So we can say that generally speaking, if a disk is rotating in a magnetic field, the magnetic field is changing. We know Faraday's law of induction, and that means that when there is a changing magnetic field, it will create an electric field. And we know that in copper, because it's conductive, the electrons can move freely, and an electric field will move them. That will be a so-called eddy current induced in the disk. And we know that when a current flows in a magnetic field, the Lorentz force will act on these currents. And the Lorentz force will apply a torque on the disk, and that will be the main reason for the deceleration. Now, where can the rotational kinetic energy of the disk go? It will be dissipated as the resistive heat, or the Joule heat of this phenomenon. And eventually, this will be the reason for the deceleration of the disk. So let's see how I measure. As I have mentioned, I wanted to measure the deceleration of the disk. Now, to achieve that, I used this fixed axis gyroscope with a live gate. I attached a little piece of paper to the side of the disk, so each time it made a rotation, it triggered the live gate. Thus, I could measure the time of each revolution, with which I can calculate the angular deceleration. And I used the drill for the acceleration of the disk at the beginning of the measurement, because with that I can achieve a constant starting angular velocity. So I derived many parameters of the disks, including the material. I used mainly copper and aluminum disks, but also tried with surgical steel, because that's non-ferromagnetic as well. And I derived the thicknesses of the disks from 1 millimeter up to 4, and also changed the radius. I have bigger ones and smaller ones. So let's see this basic demonstration of the phenomenon. I can plot the angular velocity time functions. We can say that it took the magnet approximately 15 seconds to stop without the magnet, and we can see the different materials behave very differently. For example, with the magnet, copper stops in 1.8 seconds, and aluminum significantly faster, 0.4. But to be able to compare different cases, I switched from using angular velocity time functions to angular deceleration, angular velocity functions. Because, as I have mentioned, the angular velocity can be constant, but the stopping time of the disk is not necessarily the same in every case. So, the angular velocity, angular deceleration functions were definitely a note, because it's not obvious to read. We can say that here's the start of the measurement and there's the end, because the angular velocity decreases. So let's see my methods. I made always two different measurements, one with a magnet and one without a magnet, because what I care about is the decelerating effect of the magnet. So if I make a measurement with a magnet and one without, we can see that with the following method I can get the pure effect of the magnet. So here are two plots. Here we can see the two cases with the magnet and without, and here's only the pure difference. Now let's move on to the basic theory of my experiment, my measurements. So let's see at first a qualitative one. We can say that the rotation causes a changing magnetic field, as we have talked about in the basic physics. So we can see that this induced electric field will be proportional to the angular velocity, because if it's larger than the magnetic field changes faster, and also it is proportional to the strength of the magnet, because if it's higher, obviously the change is bigger. And we can say that the electric field causes this current, and this will be also proportional to the conductivity of the disk, because if it's lower, obviously bigger currents can flow in. And from that we can say that the lost heat will be proportional to this formula. And also we can say that the lost heat will be the time derivative of the rotational kinetic energy. From which we can say this proportionality, and this can be rearranged to this form. So we can see that the angular deceleration is linearly proportional to the angular velocity, and I named the ratio the rate of deceleration, and I marked it with a capital gamma. At first, we already saw some angular velocity, angular deceleration functions, and this linear dependence can be observed nicely. Now, to get something for the angular velocity time functions as well, this formula can be rearranged to this form, and here we can observe the exponential decay of this phenomenon as well. Now, we have a proportionality for the gamma from this equation, and it can be already measured, though not quantitatively, only qualitative observations can be made, but I made them. So at first, we can say that this ratio of the density and the conductivity is the only materially part of this gamma. So basically, when I have an angular velocity, angular deceleration function, and I divide it with this ratio, I should get overlapping functions even for different materials, as I did here. And we can say that the copper and aluminum case is overlapping here. And let's see the second thing we can observe, this quadratic proportionality of the gamma and the magnetic field, the strength of the magnetic field. And here's also a qualitative observation that it is indeed quadratic. But this dimensional analysis I made in the basic theory part is good for telling some phenomena occurring, but does not yield quantitative results. So in the next part, I moved on to a more advanced theory. I had to make a few approximations to do this. At first, I said that the disk is thin, so I can use a two-dimensional model, and also I approximated the magnet with a dipole. So if I can write up Faraday Maxwell equations, Faraday's law and Gauss's law, and I have to have a boundary conditions because the currents cannot flow outside the disk. From these three, the equations can be numerically solved, and from that the lost rotational kinetic energy can be calculated. For that, I made a numerical simulation in Wolfram Mathematica, and basically the input of this simulation is the geometry of the setup, the material parameters, and the magnetic dipole moment, and the output is the rate of decay I have talked about earlier. And here's one of the results of the simulation. Basically, you can calculate the currents flowing in the disk. So let's see the verification of this advanced theory. Here we can see that the blue line marks the numerically calculated result, and also I measured this gamma, basically the slopeness of the angular velocity, angular deceleration functions, and I plotted them together. We can say that the measured data shows a pretty good correlation with the theoretical line. In this case, I changed the distance of the magnet from the axis, and in the second case, I changed the distance of the magnet from the plane of the disk, and also we can see that the theoretical line shows a good correlation with the measured data points. So, to conclude my presentation, at first I successfully managed to create a qualitative theory from which I could already make several good observations, including the quadratic proportionality of this rate of deceleration and the strength of the magnetic field, and also the linear dependence of the angular velocity and the angular deceleration. Also, I could observe the material parameters in this qualitative theory. Then I moved on to the more advanced part of my theory, from which I could get results even for the distance of the magnet and the plane of the disk, and also the distance of the magnet and the axis. So, to summarize my presentation, my task was to create a gyroscopic Teslameter. We can say that this deceleration is indeed dependent on the strength of the magnet, but not only on that, but also the inhomogeneousness of the magnetic field. Because obviously it's proportional to the changing of the magnetic field, so it's not only dependent on the pure strength of the magnet, but also the shape of the magnetic field. So this method cannot use to directly measure the strength of the magnet, but can yield results concerning the magnet. So at first I talked about the basic physics of this phenomenon. I talked about my measurement setup, my measurement and results, how I handled my data. I made a qualitative theory and then a more advanced numerical theory, and after that I verified the. So thank you for the attention.
Questions from the audience? I would like to ask, do you think any magnetic material such as iron has any difference with the materials that you value?
Well, at first I must point out that the task said that I have to use non-ferromagnetic materials, and obviously in case of a ferromagnetic material such as iron, the material can be magnetized.
Okay, thank you. Have you, sorry, in slide 13, do you clarify why is using a 2D model for your approximation valid?
I can show you my appendix dia for that. Here, I have made measurements with different thicknesses.
All right, yeah, I see that. It's similar. All right, thank you. Also, just on the deceleration force at a magnet, which couple of parameters do you think is most important?
Sorry?
Which few parameters would you say is the most significant?
Well, obviously the strength of the magnet, and also the position of the magnet, and also the resistivity and the density of the material used for the disk.
Okay. In slide 16, can you just explain briefly qualitatively why does the rate of deceleration drop when it's at the edge?
Because in that case, basically there is no place for the creation of the eddy current, because we are on the very edge of the disk.
And also, one last thing, have you varied the thickness of the disk?
Yeah, I showed that appendix here just right now. Should I?
But wasn't that showing the 2D model?
Well, I verified the 2D model. Sorry. I verified the 2D model by measuring the different thicknesses.
Okay, thank you. I think here, sorry. Yeah. Hi, my name is Vinci, and I'll be opposing Hungary on problem number 12, Gyroscope Teslameter. So, I've highlighted some keywords here, so I thought that conducting non-ferromagnetic material, they've competed in varying those materials, and also I've highlighted deceleration, and they've done very well on evaluating the deceleration and parameters that they depend on. So theory-wise, they have got a good understanding and have good qualitative explanation of eddy currents and Lorentz force, but I'd like to ask them also specifically on whether the direction of eddy currents would vary this force. And they also had this good mention of the energy conservation that energy dissipated is in the heat of in the resistive heat of the spinning plate. And also they used differential equations and numerical solutions to show their points. However, in the 2D model, I believe that in slide 13 that they were accounting, they did show us in the appendix of the effect of the thickness, but they didn't show that I believe that was just showing air drag, but I'd like to clarify on that. They also have not accounted for the shape of the field. Experimental-wise, it was a good decision for them to use light gauge for precision, and then they also used with a piece of paper, they measured the angle of the rate of deceleration, and then they also obtained a effect of magnet through control measurement and without the magnet, and also they had good mention of the conductivity and density and variation of those. The quantitative theory does seem to verify the advanced theory, but I'd like to clarify with the reporter on some of those points. Experimental-wise, though, I thought that the disk was really small, and they did not seem to vary the radius, or they did not mention that anyway, which I thought having a very small radius would have a very large error on the experiment. It would be better if we use a different radius of the plate, and they were also lacking error analysis, as I was mentioning just now, about the significance of certain errors that they used in the experiment. So I'm going to ask some of the questions, such as surface drag, magnetic field angle. I'd like to ask them on the effect of that, and some of the drag force parameters that it depends on, such as the radius of the plate, such as the velocity and the thickness, and perhaps also AC, because that is a type of changing magnetic field, which I haven't seen them do in the report, and also the least current density, and I'd like to clarify on that. So, do we move on to verify the opponent to discuss on certain response? Yeah, so firstly, I'd like to, could we talk through the qualitative explanation? So specifically, for example, for a field that is, so if you imagine this is 3D and this plate is moving past this magnetic field, right? This magnetic field is going around. Okay, so are the energies, yeah, so obviously any current is generated on this surface.
At first, I would like to point out that this was not my setup.
Oh, so sorry, how was your setup?
Yeah, we moved mine. I placed the magnet here and the disc just above it.
Yeah. So it goes on one side.
Yeah.
Okay. So
and we can say that the magnetic field looks like somehow like this.
Yes, okay. For single magnet, yes, I do agree with that.
And obviously, where it crosses the disc, the vertical component of the magnetic field will create a horizontal Lorentz force.
Yes. Do you think the direction of the eddy currents generated? Is there going to be an effect? So which direction are the eddy currents?
It's symmetric, so if I change the direction of the magnet, the eddy current will flow in the other direction, but it will be the very same time I observe.
Oh, yes, but okay. So just to explain this concept, I just want to clarify. If we have this this metal strip moving past this metal plate moving past this point, you agree that it's the fact that it's a changing. So, for example, this part of this metal is moving into the magnetic field, which means that there's a change in magnetic field strength, and hence there's a eddy current generated. Yeah. So, for example, for this point, if it's moving into which direction is the eddy current going to?
Okay, so
if this way, if the field lines are say going that way,
that way, yes, then in this direction.
Why do you think so?
Because I can easily be mistaken. So the force will point in that direction. So I would say, well, it's not really the case I measured, because the disk is rotating and not moving into directly the magnet.
Oh yes, but this is actually essentially doing the same thing, isn't it? It's but in rotational movement.
Okay.
So yes, so what I'd like to just clarify that, like the direction of the eddy current is, yeah, I do believe that you're correct in that.
Yeah.
Okay, so sorry guys, just go to the next point.
Oh, okay.
Yeah, I didn't really for that. So just error in experimental wise, what do you think is the error of your using that small radius unit?
Well, obviously in that case,
Because it seems like the radius is quite small.
yeah. So if the radius is small, obviously the 1 millimeter error of the placement of the magnet is relatively bigger than in the case of a.
Could you give a percentage error, an uncertainty, like how big would the uncertainty be in percentage?
Well, obviously bigger than in the case of, I don't think I'd like to quantify it here now for you.
Alright, okay. Because could you give me an approximate radius of the that you use?
So I basically use 2 centimeter radius and also 1 centimeter radius is for the placement of the magnet.
How big is your magnet, sorry?
Sorry?
How big is your magnet?
Below 1 centimeter.
Below 1 centimeter. So for like the
Yeah.
So the
I,
of the magnet.
Okay, so I think I'm clear enough on the point that when I change the position of the magnet, I always use the bigger discs. Okay, so
you just have bigger discs.
the smaller ones are basically qualitative observations.
Also, so you do have bigger discs.
Yeah. Of course, I think I can show a picture of it. Could you please? Yeah, that one. So that's fine.
Oh, so you have always used that disc. Okay.
When I move the position of the magnet, of course.
All right.
I agree definitely that in this case,
I do think
pretty high.
There could be some error in using this very small disc. Also, experimentally, do you think that bit of paper would cause any, actually would cause any effect on the phenomenon that you're measuring?
Yes, obviously the drag force can be accounted, but I would like to point out that I basically eliminated all of these effects when I calculated the difference of the case with the magnet and one without the magnet. So in my actual results, I don't have to deal with the drag forces because that's already moved out of the data.
Okay. I do agree with you at that point that your the effect of the data is quite minimal.
Yeah.
So can I move on to the next point? So shape of field wise,
I think.
why did you choose to do a field like this instead of a uniform metal field, say through like the metal strip to the metal plate? So why would you choose to set it that way or that way? I mean, why do you choose to set this way over that?
There is no particular reason for that.
Have you investigated that? If you have different magnetic field shapes,
in this case, the field would be much more homogeneous in this case. And as I have pointed out in the summary of my presentation, the phenomenon is not only dependent on the strength of the magnetic field, but also the inhomogeneousness of the magnetic field. So in this case, I think that the phenomenon couldn't be as well observed as in that case.
I disagree with you on that point, just because I think that obviously this, if you're varying this height, this magnetic field actually changes very exponentially.
Yeah,
but this one wise, obviously you get your field lines here in the middle.
Yeah,
And
but
in
my evidence theory part, I did account for this as well, and I can show you the formulae I used evidence theory. Here. Okay, so basically this is the formulae for the field of a dipole magnet, as I have assumed it to be.
Yeah. Because the thing I was thinking about the shape of the magnetic field, the most important thing that this changes on the phenomenon is the fact that the eddy currents generated are going to be of different magnitudes. That's why different magnitudes of eddy currents can cause a different decelerating effect on the phenomenon.
Yeah, I definitely agree on you that I agree with you that the shape of the magnetic field is definitely important. But basically, measuring the shape of a magnet is not an easy task.
Yes,
so my best chance would be to assume the magnet to be a dipole magnet and calculate it this way.
On the other hand, I think perhaps using a uniform magnetic field remove a part of the disk would be a perhaps easier way to
But
calculate.
not necessarily, because field lines go this way as well.
Yes.
Obviously deeper, but still. So I don't think that it would be significantly better.
Yeah, I guess we disagree on that one, but we move on.
Okay.
Yeah. So surface drag wise, so you got this plane moving around in circles. Have you considered surface drag?
But I think, as we have discussed it already concerning the little piece of paper.
Oh no, like surface drag. As in, if you imagine this is a plate, so the drag that comes along against the surface of the disk.
Of course, but this effect is also present with the magnetic case and one without the magnetic case.
Yes.
Therefore, this effect is also moved out of my data. You see?
Oh, okay. I just checked that because I don't think I
So basically, we would like to see.
So like your accounting of the surface drag, and did you say?
In this case, basically, it's. But I wrote friction, but it's every other effect that slows down. It's the axis friction, the air, the surface friction.
Do you think it's proportional? How do you model it? Do you think it's proportional to velocity or velocity squared?
But I don't have to model it.
So how do you take account of it?
I take account it. I take by eliminating it from my data.
So how did you eliminate it?
It's like
Could you just quickly explain?
basically,
Yeah.
you can say that there are velocity-dependent parts in the torque of the torque that slows down the disk.
Yeah.
So there are parts present in the magnetic case and the non-magnetic case, and then there is the magnet. And because I want to measure the case, the effect of the magnet, I basically get the difference of the two cases, right? So basically,
okay, I think I see what you're doing there. Like this, I feel like this could be different with resistance.
Why?
The surface drag.
It's also angular. It's also velocity.
So, but like how, for example, how did you maintain the first initial velocity as the same? Like
But I use, as I said, I use the drill. And
so
the
you always
drill,
get it up to the same velocity and you get it. Okay, I see. And then you compare that data with your. Okay, I see. I agree at that point. So just last point on variation of. So if you move back to slide 13, I think I the current density. Oh, sorry, slide 16. Sorry, 16. So yeah, because I was wondering why was there a drop? Because I know you said that there wasn't enough space for it.
okay. So basically, let's say here's the disk. And if the magnet is here, for example, these eddy currents can be created pretty easily because they don't cover really high surface of the disk. Basically,
Yeah, yes,
a couple of square centimeters. But if the magnet is here, then how can
I see.
can be
Yeah,
calculated?
Okay, these points here. So then the opponents 1 minute is more.
In conclusion, now we have discussed points on the qualitative explanation and the error analysis of their experiment. I've also talked briefly on the shape of the field and the effect of that on the phenomenon, and as well as the surface drag, and also some variation in the radius of the experiment, which I thought was good. I thought the error bars for some of the discs, for the small discs, were quite big, and the reporter did agree with me on that. And also, however, I didn't see any variation in the shape of the magnetic field, which I thought could help prove that their model works for any sort of, like the magnetic field strength locally could be modeled more accurately and check that that equation is correct. We also agreed on the initial velocity of the disk is kept constant, but I thought that the reporter also lacked some qualitative understanding
Okay,
of
thank you.
any curves.
Question for you.
Thank you, reporter component. First question, I want to ask about the problem statement. The problem statement says that a gyroscope Teslameter, and the gyroscope should rotate in 3 dimensions. How do you think that will affect your phenomenon?
Well, obviously,
You'll have a short answer.
well, I think it's negative. The effect would be like should be negative.
What do you mean by 3D?
Like this gyroscope is not fixed at both ends. It will like the axis.
Oh, you mean it will wobble?
Yeah.
Well, it will change the angle of the magnetic field.
Also, the problem statement says
mean by the magnetic field, the shape or the strength?
Oh, straight.
The strength, yeah. I've shown you the quadratic proportionality with the rate of deceleration and the strength of the magnetic field. So from that, we can conclude.
Okay, thank you. For example, on this page, where does your theory line come from? Why is it like curvy? Is it like a smooth line?
Well, as I have said, it's a numerical simulation for quite difficult equations. So I would say that it's the numerical error. So I would say this is the numerical error of the simulation.
Okay. Then Tony, you mentioned that the reporting explains errors. Can you explain, for example, why this graph has errors?
What?
Or why the first part of the graph has a greater error than the second part?
Oh, simply because well, I don't see any radius. I don't see any difference in error bars here, but if there is some, I can imagine because the radius is smaller.
So the error bars come from the placement of the magnet, and these offsets are either due to the approximation of the two-dimensional model or the assumption of the magnet to be a dipole.
Okay. In your theory, do you just have one single torque?
Basically, the torque that slows down the deceleration, and I have eliminated the torque of the friction, drag, etc.
Okay. Did you measure the eddy current distribution within your disk?
Well, I don't think that there is a quantitative way for that, but the simulation yielded the shape of
the opponent. Do you think that there's a way for the opponent to model this distribution or experimentally test it?
It would be fairly difficult, but potentially is a way that you put some sort of grid through a conducting grid, and then you model the eddy current, force eddy current going in some direction like that.
Okay, thank you.
It would be a difficult one.
How do you quantify the magnetic field of a single magnet?
In my equations, there was this D0. This is the vertical component of the magnetic field, exactly 1 millimeter above the dipole. And from that, we can already calculate with the formula for the dipole's magnetic field, the shape of the magnetic field. Yeah.
Today I'll be reviewing number 12, Gyroscope Teslameter. So the problem statement, from the problem statement you can see that it wants us to investigate why the magnetic field slows down because of the spinning gyroscope, and then investigates its deceleration. And then lastly, we can test how loading parameters affect this deceleration. So for the reporter gave a basic physics explanation of the phenomenon and said that the changing magnetic field will change the electric field, which will induce an eddy current, and with the Lorentz force will change will affect the deceleration of the gyroscope. And they had an interesting analysis method for light gate, which we thought was very effective. However, the problem statement did say gyroscope Teslameter, which both included the 3D motion of the gyroscope and the Teslameter function. However, and also in the theory, they talked about the electric field, the magnetic field, angular velocity, and then how that leads to the deceleration. And they had a more advanced simulation after their basic theory. However, they didn't explain the origins and the physics of the equations, or the limits and assumptions of the theory are not fully explained and qualified. And in their experiment, they did test material, the thickness, radius, strength of the magnet, and position of the magnet, and they isolated the effect of the magnetic field by testing for friction, and they tested many parameters. However, they didn't explain their errors very clearly, and the origins of the theory curves were not clear, since some of the theory curves looked like they were smooth lines. And for the opponent, in the presentation, they emphasized the surface drag and talked about the direction of the magnetic field, and brought up different parameters that the reporter had considered. And they brought up the direction of the eddy currents, and they pointed out these parameters, which is a good thing, and they offered their own opinion on the change in the magnetic field. However, they didn't mention the key aspect of the problem statement, which is still the Teslameter and 3D motion of the gyroscope. And they didn't emphasize why their points were important. For example, why they wanted to talk about surface drag. And they could have better time management and explain this further in the presentation instead of leaving more time and then their presentation. In their discussion, they discussed the eddy current direction, and the reporter clarified it by drawing a diagram on the whiteboard. And I believe that they should also point out position and direction of forces acting on the disk for deeper understanding. Next, they talked about the shape of the magnetic field. And the reporter said that yes, that's important, but not an easy task to measure, and so they assumed a dipole magnet. The opponent said that the easier way to measure would be to model it would be using a uniform magnetic field, and I believe that the scale of the magnet and disk depends on the scale and magnet of the disk, and then might not simplify the forces into one single torque like I asked in the simple questions. And they also talked about the air drag, and the opponent emphasized its importance. And they said that the reporter said that it's proportional to angular velocity squared, and they only tested it experimentally. I believe that they should identify the origin of the resistance and explain that peak at a certain rotational velocity. And they also discussed the size of the disk or the area of the small disk radius. And here I believe are the points missed. But first, I want to talk. I believe that they should talk about the 3D motion of the gyroscope, because since the gyroscope is 3D, the direction of the magnetic field will be constantly changing due to a change in the axis of rotation, and the current model is insufficient for a complete analysis of the complete gyroscope. And they also, I asked about the measurement of eddy currents, and then eddy currents influence the Lorentz force, which together changes the deceleration, and I think they can try to test that. They also didn't talk about the limits of the theory. For example, if the magnet is too large, they might lose a portion of the force they created, and a non-ideal field distribution might be created due to attenuation. And they should explain the error for precision. For example, the further away, the less effective magnetic field caused by the magnet, and they should consider a distribution of torque instead of using a single torque to approximate it. And also, they talked about the thickness of the disk, and the reporter said the thickness of the disk does not matter, but I believe that since there are eddy currents in the z direction, increasing thickness will increase the amount of eddy currents, thus impacting deceleration. Thank you.
Final remarks?
Okay, thank you for this excellent fight and review. So at first I'd like to point out that the opponent talked, and both the reviewer and the opponent talked about the two-dimensional model. Now we can say that if the disk is very thin, as it was in my measurements, you can say that currents will only flow relatively in the plane of the disk. Therefore, if we see the acting Lorentz force, it will be always horizontal. Therefore, I don't expect torques other than the one that slows down the deceleration. Now, about the shape of the magnetic field, it is here the formula for calculating the shape of the dipole magnetic field, and it is included in my advanced numerical theory. Also, I have mentioned this gyroscope. Why don't I expect torques other than the ones slowing down the gyroscope? And you have mentioned the limits and assumptions of my theory. I think I was quite clear on that, obviously the boundary condition is that the currents cannot flow outside of the disk because they can't, and also that I approximated the magnet of the dipole, and basically yes, those. So here's the thickness variation, which verifies, in my opinion, the two-dimensional model, and here's the current density. You talked about it, that maybe I could have measured it. The theory yields these results, and thank you for the idea with the coil. It's actually can be working, though I think that these currents are not very large, so it must require a sensitive measuring device, but it's a good idea, definitely. So thank you for the fight, and thank you for the review. It was great.
Questions from the jury? Yes.
Could you please show slide 16? The question how the errors are obtained on this slide.
Yeah. So they basically come from the placement of the magnet, because I could place it with one.
No, not on X, on Y. The errors on the rate of the acceleration shown by on Y-axis shown by blue.
Okay, so basically if I can't exactly place the magnet, then obviously there will be a change in the magnetic field in the plane of the disk, which means an error of the placement of the magnet can be accounted in the y-axis.
How you got these figures? So you measure whatever, 10 times with this?
Yes, basically there are more measurements, and I calculate averages.
And why the errors are the same for all points?
When they are not necessarily the same, they just close to each other.
Okay, thanks.
Just to clarify the issue, you mentioned that this decelerating because Lorentz force stop. Am I right?
Yeah.
So what if we have ideal magnet, for example, ideal material, for example, superconducting?
As superconducting material.
So we still have the Lorentz force which act on the charges, but we have.
In that case, we can say that this rate of deceleration. So basically, the
I mean, what is the reason of the, what the torque? Where is
Okay,
the
so in my equation we could see that the rate of deceleration is proportional to the ratio of the conductivity and the density. Now, if the conductivity is infinite, then the rate of deceleration should be infinite. I think that.
But the conductivity is just scalar. It cannot change the direction of the torque.
Alright,
Well,
we should maybe move on, yeah.
Maybe-
I have a question. So your model relies on the dipole.
Yes.
How did you find the dipole strength for this?
with a Hall sensor.
So did you do a calibration or did you test whether your magnet fits?
Well, I took a Hall sensor and I placed the magnet next to it for 1 millimeter, and thus I could measure the strength of the magnetic field, because the Hall sensor basically measures the magnetic field.
Yeah.
Okay.
Please,
Yes.
question. Your numerical work, you show the Maxwell equation, but it's unclear what equation you put in your numerical work. It's you
Faraday's law of induction and Gauss's law, and obviously the
yeah,
boundary.
but what is in a numerical simulation?
Sorry?
What's the equation you use in a numerical simulation?
Faraday's law of induction and the Gauss law. And
Yeah,
obviously the
how do
boundary.
you combine those?
So from the Faraday's law of induction, from
I
the
understand that, but how? Yeah.
from the magnetic field, we have the magnetic field and we have the rotation. From that we can calculate the electric field, from that we can calculate the currents, and with the resistivity we can calculate the lost heat.
Okay.
Nobody else? Yes?
Another question to the reporter. So among non-ferromagnetic material, we should distinguish two kind of species, diamagnetic and paramagnetic. In theory, can account this issue? How could you, at least qualitatively, mention what is the difference between paramagnetic and diamagnetic material? Because they both non-ferromagnetic, obviously.
Ferro and diamagnetic?
I mean, diamagnetic material and paramagnetic material.
Paramagnetic. Okay.
So,
I don't have they would have a significant difference.
okay, significant, okay, but I mean, where we should expect with more deceleration or less deceleration?
I don't think I can answer that here now.
A question for the reviewer. For points missing, what is most important point missing from your point of view, and how this missing point, if you do it, can improve the report?
I believe that it is the limits of this theory, because it didn't explain in which boundary theory exists in.
Okay, thank you.
Yeah, I'd like you to answer to the reviewer about the 3D nature of the problem. How do you answer to that? You know, they make a big point about that, right? The 3D
The question just?
to the reporter.
Okay, so in my final words I pointed out that because the disk is relatively thick, I expect currents only flowing in the dimension of the plane of the disk. Therefore, the Lorentz force will act only in the plane of the disk. So basically, I don't expect any other force acting on it, inclining it towards any other direction.
I think that because, as I mentioned, the changing axis will change the direction of the magnetic field, and the field's relative position will change by time, so it would give us more dimensions for measurement.
Okay. Thank you. Ask what you write down the grades. 7, 5, 6, 7, 6. Then the grade for the opponent. 6, 5, 7, 6, and 5. And then finally for the reviewer. 7, 7, 8, 7, and 6. For the reporter, we're between 7 and 5. Maybe, Elia, could you start with the
Yeah, I
justification?
think there were a few things, including the error analysis, that were not too clear, the explanation. So also, I think you did a good job in terms of your theory of the limiting factor, but at the same there are some obscure part of the presentation in terms of the physics that didn't convince me.
Okay. So I gave you a 7. I thought there was some decent investigation of the problem. But as mentioned by the reviewer, you of course limited the scope of the phenomenon, which is fine to a certain extent, but I thought that you could at least try to investigate something more into the direction of a Teslameter. And secondly, the determination of all these other torques of friction and also how you calibrate your magnetic field strength was not really transparently shown in the presentation. So it was very good, but I mean there you could still improve to make it clear how you model. Yeah. And then there are also some other issues, like for example your domain of your disk has a hole, because you are assuming you drill some hole and then there you have you mount it. So there are some aspects where you should be maybe more clear. Do you wish to add?
Yeah. I like the way you present results with different materials and which can be fit on the single slide and showing that this proportionality works fine.
Okay, for the opponent, again between 5 and 7, we had 2 5s. Maybe could you just
My grade was just because in a report, in my point of view, there are still a lot of room for physics discussion. Some of them I just trying to ask about the material because we only played with the reporter played only with the conductivity, but of course they also have magnetic accessibility or magnetic permittivity. And we can differentiate between, for example, copper, aluminum, and for example, the mercury, which is diamagnetic. So you did mention. And of course, still, I'd like to see more physical explanation from the point of view of torque, because as I mentioned, if we have ideal case, so still the torque can change its direction, but we have no anticipation, so I can't understand where this torque should be directed. That's I mean that you did not best job as the opponent. And that's why I don't rate you in comparison with this, because I still there is a lot of things to discuss even from physical point of view. But that's why I may mention so.
yeah, sure.
1, 0 from my point of view for relevance of questions. So it was relevant. 2 for opposition speech. Of course, we gave pretty clear, consistent analysis, and 1.5 discussion with the reporter. Some points you mentioned with this homogeneous field, which could give us some kind of hint of the spatial distribution of the eddy current, and in fact, this model, mathematical model, could give us in principle the distribution of the model. But of course, there is another issues, mathematical issues with this dipole model, because I think that it's not totally correct.
Okay. Maybe for the 7, just a few words. Yeah.
Yeah, I think you did a very good job in opposing in terms of discussing. I've seen some fights where you get in boxing gloves, it would be better. So it was done in a very good spirit, and I agree. The prioritization is something you have to take good care of, because if you over-prioritize something and you waste time on something that is not as important, then you lose time that you could have spent digging deeper. And that's a little bit, I think, where you lost marks from my side, but then gain marks for the spirit you spoke about the presentation, you spoke to the points of the reporter, which were very good. Maybe a little bit lacking in sort of getting additional detail, but in terms of what they said, you did a good job.
Could you just continue for the reviewer, maybe?
Yes, the reviewer, my goodness. I thought it was slick. I thought it was to the point. I just look at the slides and all the information is right there, and I know exactly what there is. You brought up a lot of points. The three-dimensional rotation of the gyroscope. I think maybe a little bit less important in my opinion than necessary, but I think you did a very good job, and you didn't give up on that as well. You sort of, all right, let me dig in, let me ask this. This is important to me, and I want answers. And I thought that was very good. I think overall, and you gave time to the opposition, you gave time to the reporter. Well balanced, I thought, with some ideas for improvement. So I thought that was very good.
Okay, finally, you had a single 6 for the review.
Oh, that's again because the opponent leaves you quite a huge space, in my opinion, for the analysis from physical point of view, both the drawbacks of the reporter and of course the drawbacks of the opponent. So I think still the issue about 3D, these complicated dynamics is over. It goes beyond the standard physics because I don't understand still how elaborate some model, theoretical or even in experimental. So I don't agree that they should insist or put some pressure on this topic. Still, I rather to hear again the analysis of different materials, because not all the materials which are non-ferromagnetic still can be divided into this is basic physics, in these two groups. And the deceleration rates, of course, depends on the diamagnetic and the paramagnetic, because we know that diamagnetic still have big induction, and so that's, I think that this is quite an important point, and well, that's why I downgrade a little bit in comparison.
Okay.
From the opponent, I missed the analysis of the experimental errors from the report and the limits of the theory. Thanks a lot for the reviewer that opened this question to us. About missing points, well, it's my personal feeling, but you have too much of missing points. If you put just 1 or 2, well, for me personally, it would be better, because when you have whole slide of missing points, this is too much. I can't imagine how the measuring of currents can improve the report. That's why I give you minus for the missing points. Sometimes it's too much, but it's my personal view. Some of the juries give you
Sure.
plus, so it's.
Okay, so as we are probably behind schedule, I ask you to be really back on time, that we can continue in 10 minutes. And